we're now going to do what is called the strong principle of mathematical induction. Let me just say upfront that this is pretty complicated, and I don't expect that you will just get it the first time. So you should take this chapter as like a beginning of something that you will learn in much more detail later. You should understand enough to be able to solve the homework questions, because proofs are anyways not on the exams, and just move on, because it is complicated and there's just no way around it. It's a very intricate way of reasoning about things, and the first time you learn induction, it's hard to do it, but then as you get more and more practice, this becomes easier and easier. Okay, so what is strong induction? So let's start with induction. What is induction? Induction, you're trying to prove a statement Pn for all, let's say, non-negative, or let's say for our natural numbers. So I have a question, show Pn is true for all natural number n. If you were to prove this question by just regular induction, you would have a base case. The base case would be the smallest number that you want to prove it for. In this case, that's 0. So you would prove P0, and then you would do the inductive step, which is you will assume that Pk is true, where k is another natural number, and then you would prove Pk plus 1 is true using that assumption. And then the induction will give you everything is true. Sometimes this doesn't work, because sometimes life is just complicated. And so then you have to use strong induction. What is strong induction? Strong induction has two twists. So first thing is you might need more than one base case. So you might have something like proof P0, P1, P2, P3. You just prove these separately. There is no connection between them. There are 4 different proofs that you give. Why? I don't have a good answer. Sometimes the pattern only emerges eventually. Like sometimes Pk and Pk plus 1 are not connected to each other immediately, but after some n, they become connected with each other. And so before that happens, you just have to do regular proofs. And then for the inductive step, here's the second twist. Instead of assuming Pk is true, you assume Pn is true for all n less than equal to k. Okay, and yeah, this is very, very, very important. Or this is the thing that makes this strong induction. The base case changing is actually not that subtle. Like, okay, you did P0, P1, P2, P3, and then you did directive step. That's fine. You just did from P3 to P4 by inductive step, then P4 to P5. That's not a big deal. But this is a very drastic difference. Now I'm assuming that Pn is true for all n less than equal to k. So I'm assuming P0 is true, P1 is true, P2 is true, P3 is true, all the way up to k. So I have lots of assumptions. And from this, then I'll prove that Pk plus 1 is true. Okay, so that's the main difference in strong induction. And like I said, this is hard. I won't even pretend that it's not hard. But as long as you can do the homework problems, which are based on the problems in the book, it's fine. You should just move on. Okay, so with that, let us do an example. And you would rightly have the question, when to use strong induction and how many base cases to do. I don't have good answers. The truth is, you learn how to do this from experience. Yeah, this is now we are getting into the territory where math can no longer be taught. It is something that you have to learn by doing. Okay, so let's do an example of mathematical induction. I'm going to prove a very nice theorem. So let Sn be a sequence defined as S0 is 2, S1 is 5, and Sn is 5 times Sn minus 1 minus 6 times Sn minus 2. So I have a sequence. I give you the first element, I give you the second element, and then I give you a recurrence relation that defines all the other elements. then show that Sn is 2 to the n plus 3 to the n. So this very weird recurrence relation actually gives you such a nice closed form for Sn. Okay, and I'm just going to tell you that you have to do strong induction for this. Like one way to realize that you have to do strong induction is by noticing that you have S0 and S1 are separate, and then I should have said n greater than 1. And then you have a recurrence relation that only starts after 1. And so you have to do multiple base cases, and you have to do something more complicated. I'll do n equals 0 and n equals 1. For n equals 0, I need to show that S0 is 2 to the 0 plus 3 to the 0. The left-hand side is 1, and the right-hand, is 2, and the right-hand side is 1 plus 1, which is 2. So that gives me the base case n equals 0, n equals 1. I want to show S1 is 2 to the 1 plus 3 to the 1. S1 I know is 5. And this is also 5. So that proves the base case n equals 1. Now, when I go to S2, I can see that there's a pattern emerging starting from S2. So I suspect that inductive step is going to kick in at this point. So I'll move to inductive step. And here I'll assume Pn is true for n less than equal to k. And from here, I want to reach pk plus 1. Now, as with standard induction, the strong induction tells you what you're supposed to do. It doesn't tell you how to do it. That is something you still have to figure out on your own. So let's expand this out. Pn is true is telling me that Sn is 2 to the n plus 3 to the n for n less than equal to k. And pk plus 1 expands out too. I want to show that psk plus 1 is 2 to the k plus 1 plus 3 to the k plus 1. Okay, so now I want to go from the left to the right somehow. How will I do that? Well, I can see that I have a recurrence relation for sk plus 1. What is the recurrence relation? Sn is 5 times Sn minus 1 minus 6 times Sn minus 2. So I can use that for sk plus 1. I'll get 5 times sk minus 1 minus 6 times s. Oh, s, my bad. S is sk plus 1. So it's sk and sk minus 1. Okay, that's by the recurrence relation. K plus 1 minus 1 is k, and k plus 1 minus 2 is k minus 1. Okay, so that looks promising. Now what? Then if I notice what I have here is I know what Sn is when n is less than or equal to k. And so I know what sk is, and I know what sk minus 1 is. So I can use the induction hypothesis to plug it in there, and I'll get 5 times 2 to the k plus 3 to the k minus 6 times 2 to the k minus 1 plus 3 to the k minus 1. And this is the most I can do using the inductive step. I removed all the SKs from there. And now, if the problem is correctly designed, then everything on the left-hand side will simplify and give you the right-hand side. So I can, at this point, I still don't have a complete proof, but I have enough to start writing the whole proof and hope or trust that it will clear out when I add in the details. So let's do it. I'll say let n be a natural number. We will show Sn is 2 to the n plus 3 to the n by strong induction. The base cases, I'll do 2, n equals 0. So here we need to show S0 is 2 to the 0 plus 3 to the 0, which is 2, and that is in the question, so this is true. Then I have n equals 1. Here we need to show that S1 is 2 to the 1 plus 3 to the 1, which is 5, and S1 is 5. That is again given in the question, so this is also true. So that finishes my 2 base cases. Then I'll move to the inductive step. So here I will say, let K be a positive integer. I'll say assume Pk is true for all n less than equal to k, but I'll just expand out Pk. So I'll say assume is 2 to the n plus 3 to the n for all n less than equal to k. Okay, so that's my that's my induction hypothesis. Let me give it the name so that I can use it later. Then we will show that sk plus 1 is 2 to the k plus 1 plus 3 to the k plus 1. All right, and now it's just algebra. So left hand side is sk plus 1, which is by the recurrence relation sk minus 6 sk minus 1, which then by the induction hypothesis, this is 5 times 2 to the k plus 3 to the k minus 6 times 2 to the k minus 1 plus 3 to the k minus 1. Note that I really needed the strong induction hypothesis because I'm using induction hypothesis for sk as well as sk minus 1. So I'm using the fact that that statement is true for every integer less than equal to k, which includes k and k minus 1. If I had only assumed that pk is true, then I could only substitute sk, and I won't be able to substitute sk minus 1. This is the strongness part of your induction hypothesis, is the second piece in this equation. And I guess I'll just expand everything out. Now, if I see I have 6 times 2 to the k minus 1, 6 is a multiple of 2, so I can absorb one of the 2 in there. And similarly for the next thing, so I'll do it systematically. And now I have 5 times 2 to the k and 3 times 2 to the k, so that becomes 5 minus 3 times 2 to the k. And then I have 5 times 3 to the k and 2 times 3 to the k, so that becomes 5 minus 2 times 3 to the k. And so I'll get 2 times 2 to the k plus 3 times 3 to the k, which is 2 times k plus 1, and then 3 to the k plus 1, and that is my right hand side. Whew. Okay, so I've shown that the left hand side is equal to the right hand side. This is what we needed to prove. And so this proves the inductive step. And then I have to conclude this, and hence we have shown that Sn is 2 to the n plus 3 to the n for all natural numbers n by the principle of mathematical induction.